In the context of factoring finite state machines, let's look briefly at the high-level design of a Morse code transmitter. We're not going to go down into the low-level details. We're just going to look at a higher level how we can naturally factor this design. So remember, Morse code means sending a combination of dots and dashes. So the letter A is a dot dash, the letter B is a dash dot dot dot, the letter C is a dash dot, and so forth. When we're sending this, a dot is going to be a short pulse and a dash is going to be a longer pulse. How long are these pulses? Well, remember we measure them in clock cycles, so we might say that for argument's sake the dot might be 5 clock cycles and a dash might be 15 clock cycles. Our objective is to build a finite state machine that can be used as part of a bigger design. So we can have, let's say, 5 wires coming in. 2 to the power of 5 is 32. So I can select one of 32 letters to send. And since there's only 26 letters in the alphabet, that should be enough. I guess you need to worry about numbers, but don't worry too much about that. You can have an extra wire there if you really want. So these wires are going to select what letter to send in Morse code. I'll have a wire that signifies when to send the letter. So at the rising edge, when there's a transition, we're going to send the letter that's on these wires here. And so that's, if you like, an input wire. And we also want an output wire that gives us a pulse when we have finished sending that letter. You see, in Morse code, different letters are different lengths. And so if we want to be ready to send the next one, we need to know when we've finished sending the present one. So in terms of an interface to a larger design that might send sentences or whatever, we're going to have a finite state machine that when it's told to send a letter, it sends the letter and then tells us when it's finished sending that letter. Of course, this can be coded as just one big finite state machine, but if there's a simple way of factorizing it, then often a factored design is going to be easier to write, fewer bugs, easier to maintain, and so forth. So how can we factor this? Let's start with another finite state machine over here. Its inputs are going to be, this one tells us whether or not to send a dot. This one tells us whether to send a dash. We can connect these two finite state machines up. So now the finite state machine in red can tell the green one whether to send a dot or whether to send a dash. If both lines are 0, nothing sent. As soon as the top line goes 1, the green machine will send a dot. And if the bottom line becomes a 1, then the green machine will send a dash. But of course, the green machine has to tell the red machine when it's finished sending. The job of the red machine is now straightforward. When a start pulse is given, the red machine needs to look at what letter wants to be sent, systematically goes through the sequence of dots and dashes required to send that. So a finite state machine can record such things in memory. And the red machine then produces the correct sequence of dots and dashes to this machine here. It listens for when finished is done and then sends the next dot or dash according to what the letter is. The green machine can make use of 2 additional finite state machines. One of them is going to count the time required to send a dot, and one of them will count the time required to send a dash. And by the way, these yellow finite state machines are basically the same, they're just counters, and so you can declare it once as a module using a parameter, and then when you instantiate this module, you instantiate it with the parameter set to 5, and when you instantiate this one, you set the parameter to 15. the control lines here, one's used to start the counter and one's used to signal back to the green machine that the time has expired. So now for the green machine, if it sees it needs to send a dot, then it will tell this yellow finite state machine to start your counter, and it just waits until the time is up, signified by a 1 on this line here. Similarly, if this green machine's asked to send a dash, then it will send a 1 to this finite state machine to start its counter, and when the time's up, when the count reaches 15, then this finite state machine will send a 1 back to this one here, and this one's listening for this to be a 1, and then it knows that it's finished sending a dash. And when it's finished sending its dot or its dash, it signals that on the finished line. In closing, factoring a finite state machine implementation is no different from taking a task and breaking it up amongst a group of friends to do. So if a bunch of friends had to operate a Morse code transmitter, you could have one friend on the timer for a dot, one friend on the timer for a dash, one friend actually sending the dots or the dashes in response to another friend telling him whether to send a dot or a dash. So there's room for 4 people here. Maybe not the most efficient way to operate a Morse code transmitter, but in terms of an electronic implementation, this will give you a nice, safe, clean design that should be relatively bug-free.